Hello everyone, section 3.7, implicit differentiation. Normally I don't read all the typed out information that I have. I usually leave that for you to read and go through, but this one is an exception because we're going to follow this example and it's going to pretty much show us how to do the rest of the section. So when we're faced with an equation like x cubed plus y cubed minus 15xy equals 0, we can't just solve this equation for y, certainly not easily. There's no way to get y alone in this equation in terms of x. But that doesn't mean that we can't still find dy dx, or find the derivative with respect to x, using a technique called implicit differentiation. So this is going to show us how to do that, and then we're also going to extend our power rule to include fractional exponents later on. So if we had an equation like xy equals 1, up till now we could simply rewrite this equation to y equals 1 over x by dividing both sides by x. Take the derivative of both sides, dy dx on the left, derivative with respect to x of 1 over x. You can do it out. I would turn this into a negative exponent and then do the power rule and then bring it back down below, and you'll get negative 1 over x squared in the end. That's one way to solve the problem. It's the best way to solve this particular problem. But there is another way to solve this problem that's going to show us how to deal with a problem, an equation like this one that we see up above. So instead of rewriting the equation, we could have kept it as xy equals 1. I take the derivative of the left side as it is without rewriting it. This is a power rule. Product rule. It's a power rule because we're doing power rule later on. This is the product rule. Derivative of the first times the second plus derivative of the second times the first equals derivative of 1, the right hand side, is 0. Derivative of any constant is 0. So dx of x, the derivative of x, is just 1 times y, so we get y, plus dx of y is dy dx times x. So I put the x out in front because that's the way we're used to seeing it. Subtract y from both sides and divide both sides by x. I'm getting the dy dx alone. I get dy dx equals negative y over x. We know what y is equal to. Y is equal to 1 over x. If I replace this y here with a 1 over x, I'm going to get negative 1 over x over x. And if I simplify this complex fraction, I get negative 1 over x squared, which is the same result that I got up here. Now, again, I would never do this particular problem using implicit differentiation, but I can, now that I know how to do implicit differentiation, I can use that to solve the problems where I have to use it to implicit differentiation because I can't solve for y. I would recommend watching these videos by Calculus with Krista in Calc.com. If we don't get a chance to watch them during class, you should watch them on your own. Okay, let's take the time now to solve a problem together. So x squared plus y squared equals 1, and we want to find what the slope of this is a circle, at the point 3/5, 4/5. Okay, so I'm going to solve this derivative because slope is derivative. I'm going to solve this derivative implicitly, okay, which means I'm going to take d dx of x squared plus y squared equals d dx of 1. Take the derivative of the first side, of the left side of the equal sign, and the derivative of the right hand side of the equal sign. Derivative of the left hand side of the equal sign is power rule 2x dx dx. That's just going to be 1. And most of the times we write the 1, but I'm putting it this time because I want to emphasize when we do the power rule for the second term, it is still 2y dy dx. So derivative of the outer function, chain rule, 2 brings it out front, subtract 1, times the derivative of the inner function, d dx. Power rule, bring the 2 out in front, subtract 1 from the exponent, times the derivative of the inner function, which is y, equals 0, because derivative of any constant is always 0. This is just 1. So we have 2x plus 2y dy dx equals 0. Solve for dy dx, get the dy dx alone, so subtract 2x from both sides, divide by 2y, dy dx is equal to negative x over y. Okay. Now I want to take this and I want to evaluate it, so I'm going to do, sorry. There we go. I want to take this dy dx and I want to evaluate this at 3/5, 4/5, which means I want to evaluate negative x over y at 3/5, 4/5. Again, this is x, this is y, so I can plug these in. Equals negative 3/5 over 4/5. Deal with this complex fraction, and we get negative 3/4 is equal to the slope of this circle at that point is negative 3/4. Again, another video that you should watch if we don't have time to watch it in class. You should watch it here. Alright, here's an example where we could not solve this for y. I could have solved this for y. Would have had a radical in it, but I could have solved this for y and then dealt with that. But this one, there's no way to solve this for y at all. So we're going to do the exact same thing we just did a second ago. Dx of the left-hand side is 5y squared plus sine y equals dx of the right-hand side, which is x squared. Okay. Left-hand side, this is a power rule and a chain rule. Okay. So we have 10y to the first power dy dx times the derivative of the inside function, which in this problem is y. Derivative of sine is cosine plus cosine y times the derivative of the inside function, which in this case is y. dy dx equals power rule 2x dx, the inside function is dx, was x, dx, which is just 1. Okay. I have a dy dx in common here. I can factor that out. So I have 10y plus cosine y dy dx equals 2x Divide by both sides by 10y plus cosine y, and I get dy dx equals 2x over 10y plus cosine y. Now, if I knew what y was, I could replace this y and this y with whatever it is that I knew. But that's the catch-22. If I knew what y was in the first place, I wouldn't have used implicit differentiation. I would have just done the derivative directly. Okay, and that's what this note says here. Okay. Example 3, we want to find the slope of the tangent and the normal to this particular curve at the point 4, 0. So this particular curve is 7 y to the 4th plus x cubed y plus x equals 4. Again, impossible to solve this for y. So dx 7 y to the 4th plus x cubed y plus x equals dx of 4, the right hand side. Okay. Normally I won't do this, but because this one's going to have a product rule in the middle of it, I'm going to break this up into 3 derivatives. So we have dx 7y to the 4th plus dx x cubed y plus dx of x equals derivative of 4 is 0. ddx of x is going to be 1. This is going to be, again, power chain rule. So we're going to have 28y cubed dy dx. This is product rules plus derivative of the first times the second. Derivative of the first is 2x squared times the second, y, plus derivative of the second, dy dx, times the first. And I'm going to write the first out in front because it gets messy if you don't. I don't want to write it afterwards and have it be confusing. Plus plus 1 equals 0. Now I'm going to move the terms that don't have dy dx's over to the right hand side, and I'm going to factor out the dy dx from the terms that I do have. I'm going to do that all in one step. I'm going to have 28y cubed plus x cubed dy dx equals negative 2x squared y minus 1. I apologize, that's a typo. 3. Okay. Negative 3x squared y minus 1. Divide both sides by 28y cubed plus x cubed, and I get dy dx equals negative 3x squared y minus 1 over 28y cubed plus x cubed. Okay, that's the slope anywhere on this curve. I want to find the slope of the tangent at this point. So we need to evaluate this dy dx. Needs to be evaluated at the point 4, 0, which means that negative 3x squared y minus 1 over 28y cubed plus x cubed needs to be evaluated at 4, 0. Again, that's x, that's y. Everything in here is x's and y's, so I'm going to start plugging in. Negative 3, 4 squared times 0 minus 1 over 28 times 0 cubed plus 4 cubed. Doesn't even matter what 4 squared times negative 3 is because it's times 0, so the numerator is negative 1. 0 cubed is 0 times 28 is 0 plus 4 cubed is 64. And this is the slope of the tangent. Slope of the normal, second part of the question, is the reciprocal of the tangent because the normal and the tangents are perpendicular to each other. So the slope of the normal, negative reciprocals of each other. So it's positive 64. That's example 3. All right. So here's a summary of the process that we've been using. Differentiate both sides with respect to x, collect all the terms that have dy dx on one side, factor out the dy dx, and then solve for that dy dx. Get the dy dx alone. Okay. Example 4, find the slope of the tangent at this point for this equation. So again, d dx y squared minus x plus 1 equals d dx of 0. Power chain rule, 2y dy dx minus derivative of x, 1, derivative of 1, 0, derivative of 0, 0. Solve for dy dx. I'm going to add 1, divide by 2y. dy dx equals 1 over 2y. And find the slope of the tangent. Slope of the tangent is equal to dy dx evaluated at 2, negative 1, which is equal to 1 over 2y evaluated at 2, negative 1. So we have, there are no x's. It's just 1 over 2 times negative 1. 1 over 2 times negative 1. The slope of the tangent is equal to negative 1/2 at the point 2, negative 1. All right, example 5, we want to find the second derivative of this problem. Okay, so we're going to implicit differentiation. Take the first derivative, so d dx 4x squared minus 2y squared equals d dx of 9. Power rule, 8x d dx dx, which is just 1, minus power chain rule, 4y dy dx equals 0. solve this for dy dx, we're going to subtract 8x from both sides, divide by negative 4y. dy dx going to be negative 8x over negative 4y, which reduces down to positive 2x over y. And then we have to do the derivative again. So d2x dx2, second derivative of the left side is that, equals d dx 2x over y. Now I could bring the y up to make it a negative y and use the product rule, but I'm going to use the quotient rule. So d2x dx2 equals derivative of the top, 2, times the bottom, y, minus derivative of the bottom, dy dx, times the top, which is 2x, and I'm going to put the 2x out in front just because it's cleaner this way, all over the bottom squared. Now you might think that we're done, and we're pretty darn close, but I know what dy dx is. I just solved dy dx is 2x over y. So I now can put in the dy dx. I can't replace the y's. It was too complicated. There's no way to solve for the, or there is a way to solve for the y. It's going to have radicals in it. But if we replace here, we're going to have 2y minus 2x times 2x over y all over y squared. So let's get rid of the complex part of the complex fraction. Multiply top and bottom by y over y. And in the end, I get 2y cubed. I'm sorry, 2y squared minus 4x squared over y cubed. And I could actually stop here. This is fine. But one more small algebraic trick. If I notice, I got a negative 4x squared and a positive 2y squared. Here I have a positive 4x squared and a negative 2y squared. If I multiply everything here by negative, I can get 2y squared minus 4x squared is equal to negative 9. I can replace this entire numerator with negative 9. Negative 9 over y cubed is the second derivative of this original function. Okay. Power rule. When the powers of x aren't whole numbers, when they're rational fractions, we can still use the power chain rule. So derivative of x to the 4/5 power. Take the 4/5, put it out in front. Subtract 1 from the exponent. So 4/5 minus 5/5 is negative. So I'll write it just this first time. Minus 1 equal to 4/5 x. So the 4/5 minus 5/5 is negative 1/5 power. Part B. Take the exponent, put it out in front. Negative 7/8 x to the negative 7/8 minus 1. So negative 7/8 minus 8/8. Negative 7/8 x to the negative 15/8 power. Part C. Take the exponent, put it out in front. 4/3 x. 4/3 minus 1. 4/3 minus 3/3 is 1/3. So 4/3 x to the 1/3. I'm going to turn this into a fractional exponent. So we're doing dx of x to the 1/3 power becomes, put the exponent out in front, x to the 1/3 minus 3/3. 1/3 x to the negative 2/3 power. And only because the original was written as a radical, I'm going to write this as 1/3 cube root of x squared. Don't worry about rationalizing. That's an algebra teacher thing. Once you get past algebra, you don't ever have to worry about rationalizing denominators. Part E is again a power chain rule. Okay. Take the exponent, put it out in front. Negative 1/5 cosine of x to the 1/5 minus 1, or negative 1/5 minus 5/5 is negative 6/5 dx of the inside function, cosine of x. Derivative of cosine, negative sine, negative 1/5 cosine x to the negative 6/5 power times negative sine of x. And I'm just going to clean this up. I got two negatives here. I'm going to put that sine of x out in front. So I have positive 1/5 sine of x cosine of x to the negative 6/5 power. Part F. Again, power chain rule. Take the 3/4, put out in front. X squared minus x plus 2. 3/4 minus 4/4 is negative 1/4 times the derivative of the inside, dx x squared minus x plus 2. Three-fourths x squared minus x plus 2 to the negative 1/4 times derivative of this is power rule, 2x minus 1. And that's the answer to part F. Part G, again, power, chain rule again. Take the negative 4/5 exponent, put it out in front. Negative 4/5 secant pi x. Negative 4/5 minus 5/5, negative 9/5 times d dx of the inner function secant pi x. Derivative of secant is secant pi x tan pi x d dx of pi x. Negative 4/5 secant pi x to the negative 9/5 power times derivative of secant is secant pi x tan pi x times the derivative of the inside function, chain rule, d dx pi x. Derivative of pi x is pi. Secant pi x to the negative 9/5 power times secant of pi x to the first power. We add the exponents, so negative 9/5 plus 5/5. Negative 4 pi fifths. Again, derivative of pi x is just pi. Secant pi x negative 9/5 plus 5/5, negative 4/5 tangent of pi x. And that's the answer to part G. It's my Excel and bookwork for you to do. Thank you very much. Bye.